Hello everyone, and I'm going to go ahead and try to do a screencast here for the RL, RC, and the RLC series circuits. So I'm going to go ahead and start off with, see if I can draw this, RC series circuits. No, I'm better at this than I thought it was. So the first lab that you're going to do, the first part of the lab 6, requires you to build a RC series circuit and calculate the theoretical and actually measure the magnitudes of the voltage and the impedance. So let's go ahead and start off by drawing out that circuit. I'll draw it off over here to the side. So you're given something like this. You have some resistance, a capacitor in series, and that's going to ground. And of course our power source is going to ground as well. And we're given the values. We're given that voltage in is equal to 2 volts peak to peak. Our resistance is 1 kilo ohm. And our capacitance is 10 nanofarads. And I forgot to mention that our input voltage being 2 volts peak to peak at 10 kilohertz. Okay, I'm doing a lot better drawing on this pad than I thought I would be. Okay, so something that we need to remember when we just did the RC step response, the RL step response, when we were looking at how these components work together. If you can remember that series capacitor circuits, that the voltage lags current by 90%, so 90 degrees, excuse me. So let me go ahead and write that down here. And it's good for you to do also in your homework. Remember, this is going to be your homework. I'm actually going to work out the very first part of what I want you to do, and then the rest should seem easy for you. So a series, I'm going to put RC circuit, and I probably should draw in the lines. We said that voltage lags current by 90 degrees. Voltage lags current by 90. And we proved that in our previous labs. So just like I asked you to do in the previous semester when I asked you to do your homework, I want you to, and I can't find the lines here, but let me just see if I can draw one. I want you to separate your problem. Oh, good, it's kind of letting me do it, I hope. It sure isn't. So we know what the problem is, and we're actually going to write our solution. Don't forget, we haven't stopped doing this. This is actually going to help you lay out your problem so you know what you have to work with. And so we have some equations that we need to write down just so we can keep them always in our immediate reach. And that is when we're dealing with alternating current, we have something called potential, which is equal to, just like Ohm's, it is Ohm's law, but we're looking at Ohm's law for alternating current. It's equal to I, which is current, times impedance. Since now we are looking at reactive components and passive components like resistors and capacitors, we're looking at total impedance for the circuit, and so we're going to designate that by Z. And in this case, we are working only with a capacitor, so we have capacitive reactance, which is the capacitive input to that impedance, which is equal to 1 over 2 pi frequency times capacitance. All right. And then we got a couple of other equations that you are kind of familiar with, you should be familiar with, which is looking at the total voltage in the circuit, especially in this case since it's a series circuit, it's really a voltage divider circuit. it's actually equal to the voltage drop across the resistance. So in this case, the potential across the resistance plus that potential across the capacitance. So none of this has changed. It's all the same from our previous class. And remember that we have our input 2 volts peak to peak, 10 kilohertz, 1 kilo ohm, and 90. Okay, so let's go ahead and I've always asked you to write any diagrams, anything that will help you actually solve the problem, so you can actually visualize it. So what I'm going to do right now also is draw what's called a phasor diagram. You may have already been working with these. And of course we're starting here from 0, where we have current going in one direction at 0 degrees. And this one's going to be the phasor for the voltage potential across the resistor. We also have the voltage potential for the capacitor going down at minus 90 degrees, and so we'll label this EC, right? This is the current phasor diagram, and we know that the total is actually going to be some phasor going between these two. Now we don't know exactly what it is until we calculate it at some angle theta, right? And the angle is with respect to the resistance, because the resistance is at 0 degrees, right? And of course this is at 90 degrees. And for this we can also use Pythagorean theorem once we get to that point to find the resultant. So we would look at c squared is equal to a squared plus b squared. You can also put that in your solution. Okay, let's keep going down. So we're given that the resistance is in your lab 1 kilo ohm. So we can rewrite this, since we're going to be doing this in vector notation, we can rewrite this as 1 kilo ohm, which is the real part of the impedance. And so actually let's do this. Impedance of R, since we're going to be writing it in this format, plus the J component for resistance is 0, because it's not at any angle. So this is 1K, and we write this just a little nicer. 1K ohm, no, I'm sorry, 1K plus J0, and all of this is units of ohms. And let's go ahead and do the same thing for the capacitance, right? So if you plug in these numbers, I'm sure you can do this on your own, but I'm going to go ahead and just write it all out so you can follow me. 2 times 3.14. The frequency we said was, what is it, 10 kilohertz? 10k hertz times the capacitance of, and that is 10 nanofarads. Excuse me for writing cricket here. Right, and if you plug all this into your calculator, which I already have, and then you do the inverse 1 over all this, you're going to get 1.592K, or kilo ohms. And let's see if I can keep going further down. Okay. And to write this in the vector algebra formula, it will be 1 point, actually since it's the real part of the capacitance is 0 and it's going at negative 90 degrees, it'll be a minus J 1.592 K. And again, this is in ohms. The whole thing is in ohms. All right. Now we can actually turn this into polar notation, and if we did that, we would get 1.592. Again, this is just from your algebra of converting to polar notation at, oops, what did it do there? And this should be negative 90 degrees. Right. Okay. And if you wanted to actually convert the resistance into polar notation, let's see if I can put this in a place where you could see it. All right, where we have 1K, let me just draw it right up here. So this would be 1K at 0 degrees. Again, and this would be in ohms. So now we have these both in rectangular and polar notation. And what we're looking for right now is to find the total impedance of the circuit. So the total impedance of the circuit is just like you would in any series circuit. I'm going to put here, I think your lab book writes it Z of the circuit. You can also write Z total. But since we're dealing with a series circuit, it's just going to be both resistances added together. So in this case, it would be, I'm going to write it like this first so you can follow me along. XC, which is equal to the impedance of the resistor plus the impedance of the capacitor. Right. And so with that we get, let's put these both in, let's see, which way would it be better? Rectangular or polar notation? So we've done this math sheet before, so we know that we would like to keep this in rectangular format. So let's go ahead and put this down in rectangular format. 1 kilo ohm plus J0 ohms, and we're adding the impedance of C, which is 0 minus J 1.592, and again this is in kilo ohms. And again we add likes together. So I know this was kind of straightforward, but I'm kind of working out the details so you understand where all the numbers are coming from. And I know some of you could probably have done this off the top of your head and gone straight to 1K minus J 1.592. And again, keep the digits here until you get to your final answer before you determine significant digits. And so this will also be, how do we do this? We could actually just say 1. I wish I had an eraser. Maybe we do this again, because this is all going to be in K. Huh. Oh, that was cool. So it's 1 plus, dang it. Oh, this is so cool. I didn't know I could do this with the pencil. I can erase like a pencil. Alright, so let's try this again. Where are we? Where's my pen? So it'd be 1 minus J 1.592, and the whole thing would be in units of kilo ohms. Okay. Now again, the rest of it is from your algebra class. I'm not going to go ahead and review this, but if you go ahead and take the magnitude and look at inverse tangent to get the theta, we will get something around 1.88 kilo ohms at an angle of minus 57 degrees. And if you don't know how to get this, review your algebra textbook, right, of going from rectangular to polar notation. Okay, so this should actually get you started with the very first part of the lab, which is the RC series circuit. Now treat everything else basically the same way, where you're actually looking for voltage. You're going to look at multiplying these values. Now again, when we're multiplying, we know that it's actually easier to multiply if we're in polar notation. So what you'd want to do is you'd want to find the current through this circuit, and we know that current is the same across all elements in a series circuit, so that's what you want to do. And from there, you're given the voltage, and it's asking you to determine the theoretical versus the measured values of impedance for the circuit. So this should actually get you started for the first part, RL. And I'll go ahead and do another video on the, this will get you through the RC circuit. I'll do another small video on the RL. And I'm doing these in small pieces so you don't have one giant video to watch. Thank you very much.